Well, thank you very much, Chris, for those kind words. And thank you very much to the organizing committee for asking me to make this presentation. It is certainly a privilege to share with you the experiences that we've had over the last 15 or 16 years, and in particular, the progress that we've made. As this is the Hardy Address, one of Dr. Hardy's, and I did have the privilege of actually meeting Bob Hardy. Was in the area of ground hazards and working with the railroads. And hence, the title for my presentation, I think, is a reflection of where Bob Hardy has made some of his contributions, certainly within the railroad industry. First of all, before I get started, the work that I'm about to present is a collaboration with two of our only two Class 1 railroads, Class 1 being defined on the size of the railroads. That's CN and CP. The regulator, Transport Canada. The other one that's there is TTCI, which is the American part of the American railroads. The Natural Resources Canada and NSERC, and the two universities, University of Alberta and Queen's, and three consulting companies which provide services to the railroad and often share information with us, which is BGC, Clifton Associates, and Clone Krippenberger. NRC is the other part of a government agency, in addition to the regulator, that we share information with. Now, Canada currently has the largest railway network in the world. We have approximately 48,000 kilometers of track. We have the fourth largest volume of goods in the world transported by that network, and hence the transportations of goods by rail is a very important part of Canada's economy. The Transcontinental Railroad network was established in 1885 with the completion of the CPR at Craigellachie, just the other side of Revelstoke. And since that time, it's been certainly expanded, but essentially it hasn't changed since about, let's say, the early 1950s. I knew this was going to happen. So one of the consequences of having a network is, of course, it doesn't change. It remains essentially the system that we have today has been there since about 1950. And as the operations today have grown, they've grown, of course, with Canada, but particularly in terms of the magnitude of the amounts and volume of traffic that occurs on that railroad network. So what you see here is a map of the physiographic regions of Canada. And because of the size of the country and the size of the network, we, of course, traverse everything from the west coast, the mountains, into Alberta, starting with the plains, the interior plains, and then the Canadian Shield in Ontario, the lowlands of southern Ontario, and then the Appalachians on the other side. The vast amount of track, of course, is located in the western part of the country. Now, an overarching policy and driver for the railroads is safety. That safety culture today is to eliminate derailments while at the same time increasing the capacity of the system. Here we see what the industry has been able to accomplish with regards to a metric which is simply derailments. On the right is the comparison of normalized Canadian main track with normalized US. We have to normalize it because the regulators require different metrics, and so the terminology is not exactly the same. But you can see on the left the big changes that occurred in the 80s. This was primarily technology driven. Big changes to the way trains were operated and to the monitoring systems that were installed across the network. On the right-hand side is the derailments for the last, between 2001 and 2014. This is the Canadian network. So these are our two Class 1 railroads, CN and CP. And what we have are derailments per year versus on the other axis is derailments per billion gross tons kilometers. So this captures both the increase in traffic as well as what we've been able to reduce with regard to the number of derailments. As you can see, the dramatic changes that occurred in the 1980s are not going to happen. Well, now, if we want to improve the railroads in terms of trying to fix what causes this derailments, we need to look at the source of the derailments. All railroad incidents must be reported to Transport Canada, and that database is a self-reporting database, but it is obviously growing as the traffic and so on grows. Now, analysis of this database was carried out by Eric Leishman in 2017, and he used the frequency and severity. Now, the frequency is fairly straightforward. It's the derailments per billion gross tons kilometers. The severity is the number of cars that are involved with the derailment. And by plotting it in this form, we can quickly see what the big drivers are for these derailments. On the top right-hand corner, we see these rail components. The next one is really the track geometry. Track geometry is a reflection of how the track deforms with the ballast and with the ground underneath. So exactly the reasons for the track geometry deforming is not always clear, but certainly the ground must play a role. The one that comes out as number 4 in the derailment causes are what's called ground hazards. Now in the database, they are split up between rail beds and environment. But fundamentally, what is being captured is the control by what ground hazards do to the railroads. Now you have to remember that this database was established a long time ago, and the terminology in the database is not always clear. For example, washouts is a common term, rainouts is used, slides, floods, snow, ice damage, and so on. And on the environmental side, we get things like mud, boils, extreme weather events. But fundamentally, if you look at the overall reporting, you can see that most of these we would class today as a form of ground hazard. Now, ground hazards, of course, are not new to the railroads. The first official record is that by Stanton in 1897, when he reported on what's called the Great Landslides on the Canadian Pacific Railway in British Columbia. Now, these occurred in the Thompson Valley near the town of Ashcroft, and they occurred shortly after the railroad was completed in 1885. Here we have Stanton's great landslides along the Thompson River Valley today. While the slides essentially remain unchanged. The stakeholders have changed significantly. We now have a town of Ashcroft indicated with a population of 1,500. We have the agricultural community as indicated by the green areas. We have the indigenous communities, which occupies much of this 10-kilometer or so corridor, and the environment, which is a major salmon river. And so managing the ground hazards is more complex today than it was when the railroads were first constructed. If we look at the ground hazards and the physiographic regions, these are now, remember, these are ground hazards which have caused derailments, are in that database maintained by Transport Canada. We can see that the bulk of the ground hazards occur in the west, in the mountains and in the interior plains. On the shields, we get way less, and so the number of ground hazards or the frequency of the derailments are spatially distributed across the country. They're also temporally distributed. If you look at these monthly records, you can see that in the west, in the mountains, the vast number of them occur in the winter periods, with less occurring in the summer. In the interior plains, it's a little bit different. We see that the majority of those occur in the spring and summer periods, and less so in the winter periods. In the shield, they seem to be equally distributed. However, to really make progress, the impact of the railroads and their operations, the granularity of the ground hazards needs to be examined. The management of ground hazards can follow three options. These were all discussed during what was the kind of starting point for the work I'm describing here, the Kananaskis workshop in 2002, where where the railroads and their workers got together to discuss the options for managing ground hazards. We can have a reactive, and this was the approach that was carried out in the early days of the operations, I'll say the days of Dr. Hardy. Prescriptive, there is always a place for this approach. The risk-based, the proactive approach, you will see in the examples discussed, this is the direction that the railroads are heading. Now, regardless of the approach, there are some fundamental elements in a ground hazard program. First is the hazard classification. Having a clear definition improves that incident database that we report to Transport Canada. The source identification and characterization, it is not just simply a matter of identifying the hazard. For what we want to do, we need the magnitudes and frequency. Triggers, they are always essential to be able to identify when a ground hazard may occur from the point of view of the rail operations. And in those situations, having monitoring, of course, is a key component for that. And if the program is going to be risk-based, we need additional information. The consequence analysis is most important today because a simple derailment may impact many stakeholders. The fifth element is, of course, the risk tolerance. If we are to approach risk quantitatively, the risk tolerance must be declared. That is a challenge. And finally, we have what's called the ALARA process, which is basically society's risk tolerance. And that is making things that is reasonably acceptable to our state of practice. Because society changes, it is demanding and be prepared to allocate the resources to meet the tolerance guidance that challenges us all. In the slides that follow, we will see where we have made some progress. The first step was in the characterization. Basically, this is a classification system to get the terminology correct. Keegan, in 2007, proposed this generalized classifications for railroad operations to record the ground hazards. Incidents, the ground hazard incidents that we see in the database. The classification at the top level captures the ground hazards related to landslides, hydraulic erosion or washouts, the subsidence related to settlement and collapse, and snow and ice, which relates to the avalanche, the ice falls, and the frost heave. The classification in detail follows the suggestions of Cruden and Barnes with respect to all the geotechnical components. One can immediately see that if these terms have been used in the database, sorting out the severity associated with each ground hazard will be quite straightforward. So a classification system is essential for tracking the consequence associated with each hazard. In the slides that follow, we're going to only focus on rockfalls. We cannot tackle them all today. The rockfalls have received a lot of attention, and therefore they are the ones that we have made the most progress, certainly with regard to risk. Just to make the definitions clearer, so the rockfall is shown in the top right, and is basically a single block that comes from a source and then is dropped onto the track. What is also, let me see if I can get a pointer here. Okay, so what we also see is a hazard detection system. This is a simple wire that's tied into the signal system, which tells if a rockfall has made it onto the track. A rock slide is exactly what we see here, and that is just basically something that has slid off, again from a source, bigger volumes, but could equally impact the track. So I'm focused primarily on this aspect. Now, the early focus on rockfall was on the characterization side. Peckover, 1975, Bronner and Wiley, 1976, and Pito and Associates in 1977. Peckover's work was probably was the first to really document the clear relationship between rockfall frequency, temperature, and precipitation. It became recognized that while precipitation was linked to the frequency of rockfalls, the freeze-thaw cycles also played a significant role and was often the trigger. The temperature, which you see here, is when we dip into the freezing, this is the zero line, that's when we get the largest frequencies of rockfalls. Precipitation obviously plays a role, but as we've gathered more and more information, it's become clearer that the triggering by the freeze-thaw cycles that occur particularly in February and March in Western Canada is a dominant trigger for rockfalls. Now, today we know more about the rockfalls that occur along the railroads. However, the work that was done by Unger and colleagues in 1995 compiled the magnitude and frequency of rockfalls and rock slides. So he used both along main transportation corridors of southwestern British Columbia. While the new data has been added, the same general trends are observed. The volume associated with a rockfall is typically less than 10 cubic meters. These are the more frequent events, and the large volumes and less frequent are typically the rock slides. So for the purposes of when we do analysis related to rockfalls, we're essentially looking at this volume here, or this number of instabilities related to rockfalls. And as you can see on this picture, it's not necessarily the size of the rockfall that can derail a train. Obviously, the bigger ones have the bigger impacts, but these much smaller in volume can also derail a train. So getting the magnitude and the frequency correct is one of the key factors in any of these risk analysis that we're to look at. Now, one of the early works that examined the rockfall hazard was by Brian Adam and colleagues at BGC in 1998. Brian at that time was working for BC Rail. The focus was to provide a methodology for hazard ranking, an essential step in the assessment process. Now, this process is often subjective and has merit, but the outcome is restricted to that one location. Now, Pritchard and colleagues at BGC in 2005 extended the work and formalized the risk methodology and quantified the outcome. Using this approach, different sites could be compared as long as only one hazard was being assessed. Now, Pritchard suggested that the risk for what they were examining was a function of the hazard likelihood, the vulnerability, and the consequence. The hazard likelihood is just a rockfall frequency. The vulnerability is related to the likelihood the rockfall reaches the track, the likelihood that a strain strikes the rockfall, the probability of a derailment, and an additional probability of a loss term that is a function of train speed and the presence of rockfall warning system. Finally, the consequence is just basically the severity of the loss. This can be illustrated on this simple slide, what is being looked at. If you look at the cartoon on the left, on my left, in essence, Pritchard considers what is shown in the cartoon. The source of the rockfall, can the volume reach the track, the volume magnitudes at the track, and the consequence. The avoidance factor in the derailment hazard was related to whether the site had a rockfall detection system present. So in essence, this geometry reflects all that we see here. The added thing, of course, the consequence is what happens on this side once the derailment occurs. Obviously, the consequence, if it's just prairie land or if there's a main river, the consequence factor could be much greater. Now, this approach by Pritchard was an important step towards a formal assessment of rockfalls along a given section of track and led to the development of CN's hazard ranking score sheet. I don't expect you to be able to see this, but you can get a sense of the level of detail that's required to come up with this ranking. Now, as Pritchard pointed out, that based on years of experience, the approach helped prioritize inspection frequency and work priorities. And this was probably the most important contribution to this type of approach, is it formalized the allocation of resources to fix the problems that was occurring along the track. Now, similar approaches have been developed by Duncan Wiley, for CP's rockfall program. So it's not unique to one railroad. Now, a key issue with rockfalls, as we've seen on the previous slides, is identifying the source. Now, when it's a rock cut, usually scanning from the track level is often adequate to identify where the sources come, because you can see fresh release from the rockfall face. However, when you get into natural slopes that are vegetated, it is not always so clear as to where the rockfalls are coming from. In 2004, 2 rockfalls on Tornado Mountain near Sparwood, BC, traveled about 600 meters in the horizontal direction and about 350 meters in the vertical direction to reach essentially the tracks. Now, these rockfalls had a maximum dimension of 1.6 and 2.5 meters, clearly big enough to take out the train. And the masses was over 3,000 and 5,000, respectively, kilograms. Now, the largest of these 2 was found close to the track. Now, CP had been operating in this area for a number of years, so it was a little surprising that these boulders were now first showing up. So to assess this kind of a problem, Maciata at the University of Alberta developed the process model shown to evaluate the rockfall hazard under these conditions. The steps are shown in the diagram in the photo, or in the slide. And here we see a typical rockfall that we're talking about. When you encounter such a one, there's clearly no source. But to find the source, you need first a data acquisition involving LiDAR and air photos to be able to come up with a bare earth model. We need something related to the digital elevation model, the rockfall microcatchments that occur, slope angles, topographic contrast, vegetation cover. We then have to develop a susceptibility map. Where are the sources? Where may they occur? And then we need to do a three-dimensional rockfall trajectory model to be able to see whether or not it's possible to get the rock to the track. And then finally, we have a preliminary rockfall source prioritization. All of this is done within a GIS framework. So the workflow basically follows this figure here. Now, screening for the rockfall sources. So in vegetated slopes, as I said, identifying the source is not obvious. We showed that the slope angle, the slope topography, contrast, and the lack of vegetation cover are the key factors in identifying the susceptibility. And these are given those weights here when we do the susceptibility analysis. The info is contained within the GIS maps and assessed at a grid cell size of several meters. So LiDAR data is then needed to capture this analysis for each grid. Using this data and combined with the rockfall coefficient parameters, which are here, and all of these can be calibrated, particularly when you have measured data such we have at this particular site, to give you the most realistic parameters. This information is then used to answer the question, can the rockfall reach the track and with what energy? The results are illustrated with the blue lines and clearly demonstrate that most of these 3D rockfall trajectories do not reach the track. And in fact, when you walk through the woods on this slope, that's exactly what you see. The woods are full of rockfalls, but they don't simply reach the track. So while it became clear during the field program and the LiDAR analysis that rockfalls have been occurring in this area for a long time, most were not making it to the track because of the long distances from the source. Now, this is the actual source, and these are the two rockfall trajectories that ended up with the two boulders that were picked up by the train crew. So here, this is the track, and this is the trajectories that made it down. And if you remember on the previous slide, again, here's the track. All of these trajectories show that they don't make it down. So the model provided good calibration and was a way of demonstrating that even though you can't see some of these sources, they are nevertheless there. Once identified, the solution was simply a lock block wall with an appropriate length reflected by the modeling. Now, that is the random event. What I want to just give you one illustration is changes with low frequency, high impact events. This is actually a rock slide. It's not simply a rock fall. The slide occurred in 2012. It basically was 53,000 cubic meters. It covered 70 meters of track, and it buried it 10 meters deep and destroyed the existing rock shed, which is shown right here. So this is the before slide. Here's the track, and this is the after slide. There is the rock slide itself. Now, one of the things that the railroads pride themselves on, of course, is how quickly they can recover. And given the severity of this event, CN was back in service in actually 4 days. However, getting back in service is not the end of the story. The problem continues because now you have to fix the hazard while at the same time maintaining that service. And then once back in service, the final solution must be found. And this presents its own challenges, as now we have to work in the presence of maintaining train access. So after a major slope failure, the slope remains active, often with releases of smaller volumes. Identifying those areas for additional remediation is challenges in steep mountain terrain. Cromer and colleagues at Queen's University have been using LiDAR scans and photogrammetry to examine the changes in the slope since the failure in 2012. The terrestrial laser scanning and supporting remote sensing technologies combined with the geological structural mapping were used to identify potential new rockfall sources as the new rock shed was being constructed. Using the 3D change detection, they were able to identify potential rockfall sources by locating the regions where the deformations of the slope were abnormal. And here we see what areas that they had identified by getting a baseline reading of what the slope was doing and then identifying that these areas were now being in an abnormal deformations. This is not an ideal situation because of the limited access and the frequency by which you need to be monitoring. In this case, they were able to monitor the slopes periodically. In other industries, such as open pit mines, for example, we use constant scanning and radar to detect additional movements of a slope. However, in the remoteness of these areas, having constant power sources and constant access is often not a choice. And therefore, the approach that Cromer and these people at Queen's used is a practical in-between step between continuous monitoring and no monitoring, of course, at all. Now, in this study, Cromer and colleagues moved away from delivering or defining the hazard temporal probability based on magnitude and frequency relationships, and instead with the assumption that the areas showing precursor signs of failures have a much higher likelihood of failure than that obtained from magnitude frequency. And they locate, assess the volume and the kinematics of potential rockfalls before the failure occurs. Such an approach provides a baseline level of the slope behavior where trains are exposed to these steep slopes. And again, the outcome provides guidance to the maintenance crews. And here again, we see in a more colorful illustration the points that have been identified and the sizes of the volumes indicated here from 48 to 4,200 cubic meters. This allows planning for when maintenance crews are required to come in and clean up behind the rock sheds. Now, so far, we've been the various approaches that we've been used to identify the rockfall sources and assess the hazard. The approaches are primarily focused on providing input for ranking the hazards in a qualitative sense. While not focused on rockfalls, Bunce highlighted the limitations of the qualitative approach for risk assessment. Basically, the vulnerability assessment is completed for the site of each identified hazard. This includes the likelihood of the hazard influence the safety of the track, frequency and magnitude of the type of ground hazard, likelihood that a train could be impacted by the hazard, and the consequence of a train accidents, including the likelihood of a worker fatality. The assessment is then qualitatively compared to hazard and consequence information from other known ground hazards. That information is then used to help prioritize the work needed to reduce the risk. And don't get us wrong, this is an important step. However, there are deficiencies with the qualitative risk assessment, and these have been noted by Bunce. The probability of the loss of life or severe injury of a train crew, the reduction in exposure due to a hazard detection system, the influence of a track circuit on the detection, the influence of track speed on train accident outcome, the quantitative inclusion of train frequency, the potential for dangerous cargo, the presence of environmental receptors, the potential for the duration of a train service delay, and a temporal variation in the hazard frequency due to weather. The non-standardization and inclusion and omission of these 9 factors make it difficult to discriminate the difference in the consequence resulting from very large but infrequent rock slides, like the Frank slide, and a simple track subsidence issue which can be handled with a slow order. Now, Bunch used quantitative risk approach to examine the risk to rail workers for 3 scenarios, and these scenarios are indicated here. Train approach the signal to no landslide, no warning. There's a landslide occurred, the train approaches the signal, and a warning is received. In the scenario number 3, train pass signal, landslide warning not received. In each of these scenarios, which are identified here, Bunce concluded that the probability of fatality to the work crew was always less than 1 × 10⁻⁴, which has been accepted as an industry standard for workers, for geotechnical hazards. This has been done by a number of authors. Bunce also compared the work, or these scenarios, to CP's general background, both across the network and in Alberta and BC alone. In all cases, we were below what would be an acceptable level of risk. Now, if I plot this on a different type of graph, this is the annual frequency, and this is the number of fatalities. This is a standard form when declaring a tolerable risk. These levels of risk are unacceptable, these are acceptable, and these are tolerable. We reduce these with either mitigation measures to get to this level. This is where CP's data would form. So given that the risk of fatality can be quantified to a reasonable level of accuracy, consistent with the railway performance over the past 30 to 35 years, the railroad could consider the adoption of declaring a level of safety. And here we see the results from Bunce plotted on what is generally accepted by other industries. The number of worker fatalities from a single event will be low because, of course, there are only 2 crew members on a Class 1 freight railway. We also see that the Alaric zone, which represents the risk considered to be as low as reasonably practical, the residual risk is marginally acceptable, and any additional risk requires a disproportionate mitigation cost or effort, or is impractical to implement, hence the term as low as reasonably practical. If the tolerable risk was declared, the railway could then identify specific locations that contribute to the overall risk and assign the resources necessary to fix it. I'll give you one more example where we can apply this now on an operational level, again using the same approach that has been applied for other probabilities. We look at the impact of the number of rockfalls in each year and the factors to account for the number of rockfalls constrained by the ditch, and we can come up with a probability related to that particular operation. Now, this case study is actually in the Squamish subdivision, and it is along this section of track. There are no detection systems in place here. The data for such quantitative risk analysis relies entirely on the historic data. So we have the spatial distribution of recorded rockfalls, shown here. We have the temporal distribution, shown here, and also up here where we have the rockfalls plotted on the rainfall and on the freeze-thaw cycles for 2 years as examples. Massiata also considered the effect of seismic events in this particular analysis. Now, to move this forward, you need an event tree, which looks at the probability of the rockfall size, the probability that the track gets blocked, if a patrol car was sent in front of the trains. In this case, there are so many rockfalls along this section of track that patrol cars are sent in front of every train. There's only 2 trains a day. And if the freight train is the first vehicle to encounter the blocked track, and the probability that the freight train is not able to stop the speed of the train. What he found was that the annual probabilities that of a train that reaches a rockfall on a track are, of course, a function of the speed and whether or not patrol cars are present. If the permanent patrols are in place, this is the relationship between the annual probability and track speed. If there are no patrols, we will be up here. If we list this as a target probability, we can then judge what it would be acceptable for the crews when we have either of these events. These current conditions here, freeze-thaw, rainfall, the beginning of the freeze-thaw cycle, and a seismic event, if any of these are present, it would help to determine what the train operators should do with regard to putting a patrol in front of the train or not. So this just adds to the ability to be able to use the quantification in the actual operations. One final example is the QNSNL, which railroad, this is not a Class 1 railroad, but it shows how quickly things change. A fatality occurred along the rail line in 2014, and BGC were involved in developing a multi-geohazard risk along the railroad corridor. Matt Lato and colleagues in 2016 published the results, and these are shown here. Now, we're going to run out of probably time, so I'm going to just show you a couple of more slides, and then I'll wrap up. So in summary, we have a mature rockfall database that's maintained and reported in Transport Canada. Rockfalls are spatially and temporally distributed. We have empirical rating systems, the application of LiDAR and GIS technology to identify potential hazards. And we have tools to actually track the rockfall hazards and the process. I just want to leave you with these last 2. So the solutions that we have relate to rockfall detection. These are installed a long time ago, and they are still most reliable today. Other detection systems have been tried, such as seismic systems in the canyon, but unfortunately, they are not as successful as everyone had hoped. On the rockfall protection side, of course, trapping of rockfalls at the source is a key, and ultimately building rock sheds. These, of course, are extremely expensive. The work by Duncan Wiley and rockfall engineering has shown that what the limits and the application of these rockfall sheds in particular, and these types of trappings are available to us in Western Canada. My last slide is this. So in 2014, we had a terrible accident in Quebec with the Lac Mégantic, and it changed the railroad safety forever. It has to do with the transport of dangerous goods. The outcome of this accident was that Transport Canada mandated that all railroads carrying dangerous goods along what they call key routes had to do a formal risk assessment involving 28 parameters. One of those parameters was ground hazards. Now, if we look today, this headline here was actually taken from a newspaper just a week or so ago. In Western Canada, we hit 200,000 barrels per day transported by rail. Hardisty is getting set. They just announced they are doubling their capacity to fill unit trains, which are 120 cars, from 2 to 4 trains per day. So we will be doubling the capacity to move oil by rail. So we will be hitting probably 400, maybe 500,000 barrels per day, as long as we have this pipeline dilemma. As part now, we are no longer in a case of a choice. Transport Canada has mandated that our Class 1 railroads carrying dangerous goods must do a formal risk assessment, and part of that formal risk assessment is ground hazards. So we no longer have an option of what we do now. It's part of the regulated environment. So you can see how things have changed over a matter of my tenure at the University of Alberta and working here with the railroads. What we considered an option just a few short years ago is now a mandated, regulated requirement. Thank you very much for your attention.